So we then come to the part of a star's life which might seem a bit boring. Stars either live in the fast or the slow lane, and it all depends on their size. And we call it the main sequence, and we have this diagram to think about. But I want to talk about something called black body radiation. Now, imagine you've got a nice fire roaring in the grate, if you've got a house with a fireplace, and you've got a poker, and you put it into the fire, into the hot coals. Now, that poker will heat up, and what will that poker start to do, that metal, once it gets hot enough?
Glow.
It'll glow, won't it? Excellent. Now, there's a clue to what to the answers that I'm looking for now in this diagram. What will be the first colour it will glow? Red. Very good. And that, if you can get it hot enough, what will happen?
White.
Yeah, it'll actually slowly go through these colours, won't it? The colours of the rainbow. With ordinary iron or steel, I think it'll melt before you can get it blue hot. But obviously, if you've got the right materials, the hotter it gets, then the colour goes from red, all the way through to blue. Now that's basically what we mean by black body radiation. It's the radiation that a hot object gives off. And stars radiate more or less like what we call a black body. We call it a black body because if you imagine an oven, something it's physically dark, it just absorbs all the energy you chuck at it by heating it up and just re-emits it across the spectrum in an even sort of way. Now, our sun, the surface of our sun is about 5,800 degrees Kelvin or 5,500 degrees centigrade. Now this is the plot of blackbody spectrum for an object at that temperature, and lo and behold, its peak emission is in the visible part of the spectrum, and the very peak part is the sort of yellowy white region. The sun is a yellow-white star. Stars that are much cooler, let's say this temperature, 3,500 degrees, their peak is in the red and into the infrared. Whereas stars that are very, very, whoops, go back. Now, stars that are very hot, their peak is in the blue and into the ultraviolet. So what that tells us is that the colour of a star tells us the temperature of its surface, because that's what we're seeing. We're seeing the emission from the star's surface or atmosphere. And you can plot this on this diagram. So you can plot colour, which is another way of saying temperature. So the cooler the star is, it's red. If it's hot, it's blue. And what we find as well, that the mass of a star, the more massive it is, the more material it is, the more luminous it is. Which makes sense, isn't it? There's more of it. There's more gravity to compress the core and to release more energy. So it shines brighter. So when we look at stars and we plot these characteristics, the brightness of a star versus its colour, we find this main sequence here, and that's why we call it the main sequence. So all stars, for the bulk of their adult lives, as it were, they live on the main sequence, and our sun is just here. Much bigger stars burn hotter, they burn bluer. Smaller stars are cooler, and they burn, and hence are much redder. And if you look at stars in the sky at night, on a good night, use a pair of binoculars, you can see the colours. Some people can see them with their naked eye, but certainly through binoculars you should be able to see the different colours. You'll see stars that are red, stars that are blue, stars that are sort of yellow-white. So if you see a blue star, it means it's a big one. So there you are, you see. So these two guys work this out, and it's something that astronomers use as a very useful tool. So what about our sun? there it is. It shines on us every day. We don't normally see it like that, do we? So what's going on? Well, the sun is this huge ball of hydrogen and helium, and there's a core, this inner region, where the hydrogen is being fused into helium. Nuclear fusion. And temperature is about 10 million degrees, and our sun has a lifetime of about 10 billion years. A solar mass star has enough hydrogen in its core to keep going for 10 billion years. That's a long time there. A billion is 1,000 million. And we think our sun is about halfway through. So it's about 5 billion years old. So we haven't got to worry much yet. But when the sun does run out of hydrogen in its core, when this is just all helium, although the core will then collapse under gravity, it won't get hot enough for helium to start fusing into carbon, which is the next step in the process. So that'll be that in a sense. But what will happen is that the outer layers of the sun will swell up. The shock wave from the core collapsing to form a white dwarf will make the outer atmosphere of the sun swell up. Now, that's the sun size now, and that's what it's going to swell up into. It'll swell up and probably reach Earth's orbit. That's how big it'll get. Life on Earth will have long been done away with, because the sun is getting, its output is slowly going up. So in a few million years' time, or a few 100 million years' time, it'll be too hot for life as we know it on the Earth anyway. So by the time this happens, if humanity is still around, they will have gone somewhere else. So a bit of long-term planning needed there. Okay. So what gets left behind? Well, the core of the sun will shrink down and become a white dwarf, a helium white dwarf. And its size will be about the size of the Earth. It'll collapse and condense and become this quite small object, whereas the rest of the sun will be ejected out and form the red giant. Now, just to give you a scale here, if we imagine that that's the white dwarf core of our sun in 5 billion years' time, then the size of the sun as it is now would be roughly the diameter of this room, from that corner, say, to that corner. Yeah, that's about right. So that's the core of the sun. You can imagine the sun is as big as this room. Okay. Then at the end of its life, the core collapses to this size, and then the rest of the sun expands to a sphere about a mile in diameter. That's the scale. So imagine a sphere a mile in diameter. That's that image we saw, and then we're left behind with this white dwarf core. So very big sort of numbers involved.